So I am Dr. Srinivasan from Freshman Engineering Chemistry Department. So today IARE. Today we will see the chapter corrosion. So in corrosion we will see the introduction. What is corrosion? What are the causes of corrosion? Why it occurs? And there are the different types of corrosions like wet corrosion, dry corrosion. Okay, and mechanisms of those wet and dry corrosion we will see in this video. Okay, so what is corrosion? Corrosion actually it's a surface phenomenon. So surface of the metal when it exposed to environmental gases, like when it exposed to gases or other liquids in the environment, they undergo reaction. The surface area, the surface part of the metal will undergo reaction, that is it gets oxidized, and that's what we say it is corrosion. Okay, so corrosion is nothing but electrochemical equivalent of oxidation. So corrosion is nothing but electrochemical equivalent of oxidation. So in electrochemistry we say oxidation reduction. So corrosion is nothing but oxidation equivalent to oxidation. Okay, so what is corrosion? The process of decay or deterioration of metal by chemical or an electrochemical attack in the presence of conducting environment like any aqueous medium, moisture, water, etc. is known as corrosion. So the process of decay or deterioration of a metal by chemical or an electrochemical attack in the presence of conducting environment is known as corrosion. So metals undergo corrosion and convert to their oxides, hydroxides, carbonates, sulfides, etc. They will be in compound form, okay, once they are corroded. So the surface of metal begin to decay more or less rapidly. Some metals rapidly, some metals it depends on the temperature. At room temperature it will not, but the temperature is slightly increased, it will decay like that. Okay, the typical example is, we all know, is iron rust. So we have any steel or made up of iron, we have rust, which is we all know it's brown in color. It's a brown color, and its formula is Fe2O3.XH2O. Fe2O3.XH2O is the formula of rust, iron rust. Okay, so iron rust is the typical corrosion product. Rust is the typical corrosion product of iron. Okay, so which we all know, corrosion means we will immediately relate it to rusting of iron. Okay, so that is the typical example we are well known. Okay, so here it is given 3H2O. Actually brown color rust is XH2O. Okay, we don't know the X varies, and depending on the X also color of the rust varies. Copper undergoes corrosion to form a green film of basic carbonate, copper hydroxide plus copper carbonate, that is green in color. You can see if you keep the copper vessel outside for a long time, outside or in the shelf also for a long time, you can see a green color coating patches here and there. That is due to corrosion. That is due to green film of basic carbonate. Why corrosion occurs? Causes. So we all know that metals are available in the form of different metal ores are available, and from metal ores metals are extracted by metallurgical techniques. So normally metals are in the combined state, they are not in the metallic state in nature. So when they are in the ore form, like oxides, sulfides, carbonates, silicates, chlorides, metal oxides, metal chlorides, like that, they are very stable. So they exist in nature in the form of minerals or ores in the stable combined forms. We can also say compound forms. Okay, as compounds, they are like compounds. So during the extraction of metals by metallurgical way, metallurgy is the extraction of metals from minerals or ores. Okay. During the extraction of metal, these ores are reduced to metallic state, and you have to supply sufficient amount of energy to do that metal compound reduction to metal. So when they come to metallic state, they are highly unstable and highly reactive. So metallic state, it's highly reactive and energetically unstable and energetically unstable. Whereas compounds forms are less reactive and energetically stable. So metals from stable compound side, it comes to highly energetic, less stable metallic state. So when they are exposed to environment, because of its high reactivity, it gets oxidized and corrosion occurs. Okay. So hence the isolated pure metals are regarded as excited states, higher energy than their corresponding ores which are in the compound form. So the metals have a natural tendency to go back to the combined state, which is more stable, minerals or ores. That's why it forms compound formation in the form of corrosion. Okay, when metal is exposed to atmospheric gas, moisture, liquids, etc., the metal surface reacts and forms thermodynamically stable compounds. Okay. That's what we say the metal is corroded. For example, iron, it forms iron oxide dot XH2O, which we call it as commonly rust. Rust, we have all seen in a very, very common day-to-day things also. We have seen rust. Okay, wherever we have metal, iron, we have rust, we have seen. Okay, similarly copper, green color formation of copper hydroxide, copper carbonate, basic ore. Okay. Okay, what is the effect of this corrosion? So we understood that metals have the tendency, natural tendency to undergo corrosion in order to move from instability to stability. So thermodynamically, any system will move towards more stable thing. That's why corrosion occurs, which can only be controlled. A corrosion can only be controlled. Corrosion can only be controlled. It cannot be avoided. Okay, and it cannot be avoided fully. It cannot be avoided totally. Okay. So we can take precautions to control the corrosions, but we cannot avoid the corrosion over the period of time. Particularly over a considerable period of time, we cannot avoid totally, but we can prevent it. Okay. So what is the effects of this corrosion? we have metals everywhere in all industrial. Without, we cannot think of any industry without metals. Okay, any production or any production industry contains metals. So if it gets corroded, what is the effect? Wastage of metal in the form of its compound, obviously. The valuable metallic properties like conductivity, malleability, mechanical properties, malleability and ductility is lost due to corrosion. Lifespan efficiency of metallic parts and machinery and fabrication is reduced. So that's the reason in the industries they have to periodically, once in a month, every time they have to do some maintenance work in order to avoid this type of corrosion play a major disturbance. Okay. So, and also the efficiency of the overall system, production, everything is reduced due to corrosion. Obviously, because of all these things, monetary outcomes are also affected. So we will see later how it can be controlled. Corrosion, how it can be controlled, we will see after seeing this introduction mechanism of different types of corrosion and all those things. Okay, next. So theories of corrosion. There are two theories. One is chemical and a chemical corrosion, and another one is electrochemical corrosion. Okay. So electrochemical corrosion is also called wet corrosion. Okay, wet corrosion, and chemical corrosion is also called dry corrosion. Okay. Okay. Now let's see dry corrosion or chemical corrosion. This type of corrosion occurs mainly through the direct chemical reaction of atmospheric gases like oxygen, halogens, hydrogen sulfide, sulfur dioxide, or any anhydrous inorganic liquid with the metal surface. So there are three types of chemical corrosion can happen. One is oxidation corrosion, corrosion due to other gases, and liquid metal corrosion. Okay. So these are all the different types of dry or metallic corrosion. Oxidation corrosion. This is carried out by the direct action of oxygen in low or high temperature on metals in the absence of moisture. That's why we call it as dry corrosion. There is no involvement of moisture, in the absence of moisture. So alkali metals and alkaline earth metals are very highly reactive in the metallic form. So they rapidly undergoes corrosion, that means oxidation, at even low temperatures. Okay. So even at high temperatures, all metals are oxidized. If not in the room temperature, if it go little bit higher than the room temperature, high temperature means very high than the, for example, 200 degrees. Room temperature is 35 degrees, for example. So 200 is called high temperature. So at that temperature, many metals are oxidized except Ag, Au, and platinum. These are all not undergoing corrosion. That's why we use platinum wire in electrochemistry for conductivity, because it doesn't get oxidized, it doesn't undergo corrosion. Okay, so they are also called noble metals. Okay, noble metals. Okay, why they don't undergo corrosion, we will see a little bit later. Okay, so oxidation corrosion in the absence of moisture. Okay, so metal will undergo oxidation, which is similar to electrochemistry. Oxygen will take the electrons from the metals and get reduced to oxide. Okay, and metal and oxygen combine to give metal oxide, M2 plus O2 minus, or we have M2O3, metal in 3 plus and oxygen in 2 minus. Like that, metal oxides, it forms metal oxide. Okay, oxidation corrosion in figure we have represented that. That is, it is shown metal on one side. That is, this is part is metal, and this is that corrosion part. Okay, the corrosion on the metal part, and this is outside is environment. Okay, so we have inward diffusion, flow of oxide ions through the scale, and this is metal undergo oxidation according to this reaction. M gives Mn plus plus and electrons. Okay, so direction of electrons, conduction metal oxide formed by direct reaction of metal and oxygen. So electrons and Mn plus ions move towards this oxide. That electrons are taken by oxygen and reduced. Reaction at exposed part is this. Off oxygen plus 2 electron gives off oxide. In this, metal and oxide combine to form metal oxide. So outward diffusion first of metal ions through scale. Inward diffusion of means metal ions from here, oxide from this side through the arrow marks. Okay, so this is the cathode reaction. This is the anode reaction, which we have seen in the previous slide for oxidation corrosion. Okay, next. So mechanism mechanism we have seen in the diagrammatic part. Now we will see in terms of words. So surface of metal undergoes oxidation and resulting metal oxide scale forms a barrier which restricts further oxidation. For example, film means oxide formation over the surface of the metal. If the film is protective, protective means it won't allow the further oxidation because the surface is covered by the metal oxide film. So there will not be any further interaction of environment with metal surface. So it is a protective layer. Sometimes the layers are not protective, it will undergo further corrosion. We will see those things. The extent of corrosion depends on the nature of metal oxide. Okay, so that is important. If the metal oxide is stable, it behaves as a protective layer which prevents further corrosion. For example, oxides of aluminium, tin, lead, copper, chromium, tungsten, these are all comes under protective layer. And therefore, further corrosion of the metal is prohibited because they completely cover the metal as a protection. If metal oxides are unstable, the oxide layer formed decomposes back into metal and oxygen. So oxidation corrosion is not possible. For example, AgAu platinum, noble metals do not undergo oxidation corrosion. Why? Because the oxides of Au, Ag, platinum are unstable. Okay, they decompose in the moment when lead oxide or silver oxide or platinum oxide forms, dioxide forms, they decompose. They are totally unstable and decompose to metal and oxygen again. So oxidation corrosion is not possible in this metals. Okay, except these three, all other metals undergo oxidation, either depend on the reactivity, either in the low temperature or in the room temperature or in the high temperature. Okay, if metal oxide layer is volatile, then the oxide layer volatilizes. Volatile means the meaning is easily vaporizable. Then the oxide layer volatilizes after formation and leaves the underlying metal surface exposed for further corrosion. For example, if oxide layer formed, it's quickly volatilized, then again the surface of the metal is exposed. So further the metal will undergo corrosion. So this causes continuous corrosion, which is excessive in molybdenum oxide. Okay, this is an example for excessive corrosion due to volatilized nature of metal oxide. If metal oxide layer is porous, then also the oxide layer has formed pores or cracks. So in this case, the atmospheric oxygen can penetrate through the pores or cracks and attack the surface of the metal. This causes continuous corrosion till conversion of metal into its oxides are completed. For example, alkaline and alkaline earth metal, they form pores or cracks in the oxide layer, and that is the reason the environment gases can attack the metal surface still even after the film is formed on the surface due to pores or cracks in the films of these metals, alkaline and alkaline earth metal. Okay. Next, Pilling's Bedworth rule, which says, according to it, an oxide is protective or non-porous. Okay, if the volume of oxide is at least as great as the volume of metal from which it is formed. For example, the surface is covered fully with the volume of metal oxide, then it is and it is doesn't contain any pores or cracks, then it is called protective layer. So an oxide is protective or non-porous if the volume of oxide is at least as great as the volume of metal from which it is formed. If it is greater than that also, it's good. Okay. On the other hand, if the volume of the oxide is less than the volume of metal, the oxide layer is porous. That means non-continuous. So they cannot act as it's not non-protective. Okay. It's non-protective. protective layer, okay, because of porous nature, and hence non-protective because it cannot prevent the access of oxygen to the fresh metal surface below. If pores or cracks are there in the metal, we said that the oxygen, for example, can enter through the pores or cracks and get reacted with the surface of the metal, which is just below the oxide layer. Okay. Okay, corrosion due to other gases. Oxygen we have seen. Other gases. For example, corrosion due to chlorine. Silver plus chlorine gives AgCl, which is a protective film. Okay. So there are other gases like SO2, CO2, chlorine we have seen, H2S, fluorine, etc. So in this corrosion, the extent of corrosive effect depends mainly on the chemical affinity between the metal and gas involved. The degree of attack depends on the formation of protective and or non-protective films on the metal surface, which is explained on the basis of Pillings-Bedworth rule or Pillings-Bedworth ratio. We have seen just now what is that, okay, the previous thing. So that the Pillings-Bedworth ratio decides whether the, the film formed is protective or non-protective, okay. Ag plus 2Ag plus chlorine gives 2AgCl. This is a protective film. Protective film means it will further protects the exposure of metal surface to the environment. Okay. In petroleum industries, H2S gas at high temperature react with steel, which is iron, to form FeS. This is porous, okay, due to Pillings-Bedworth ratio or rule, okay. Okay, liquid metal corrosion. This corrosion is due to chemical action of flowing liquid metal at high temperatures on solid metal or alloy. The corrosion reaction is either dissolution of a solid metal by a liquid metal which is poured on that, or internal penetration of liquid metal into the solid metal. For example, in nuclear reactors, cadmium is used to control the speed of nuclear reactions because cadmium will react with neutron, okay, and thereby it reduces the nuclear reaction. So coolant sodium metal is used there in reactors. It leads to corrosion of cadmium in nuclear. Coolant sodium metal leads to corrosion of cadmium in nuclear reactors. It comes under liquid metal corrosion. Okay. Okay, next is wet or electrochemical corrosion, which is most of the corrosion that happens in nature is due to electrochemical corrosion, okay, or wet corrosion. The electrochemical corrosion occurs when a conducting liquid is in contact with a metal. When two dissimilar metals or alloys, are partially immersed in the solution. Two dissimilar metals or alloys means their the EMF difference, electrode potential difference is higher, not lower, not closer, they are higher. So when two dissimilar metals or alloys are immersed partially in the solution, it leads to galvanic corrosion. Galvanic means galvanic cell, copper, zinc, galvanic cell, like that. So galvanic corrosion, it leads to galvanic corrosion. When two dissimilar metals or alloys are immersed partially in the solution, it leads to galvanic corrosion. Okay, corrosion occurs presence of anodic and cathodic areas. That's why we call it as electrochemical corrosion. And we know that anode oxidation reaction takes place, and at cathodic parts reduction reaction take place, and we know corrosion is nothing but electrochemical equivalent of oxidation. Okay. Okay. It occurs when aqueous solution or liquid electrolytes are present. Wet or electrochemical reaction. It occurs when aqueous solution or liquid electrolyte is present. Okay. Wet corrosion takes place in environment where the relative humidity exceeds 60%. If the conditions are humid, then also the chances of corrosion is very high. Wet corrosion is most efficient in water containing salts such as sodium chloride, example under marine conditions, due to high conductivity of the solution. Okay. Wet corrosion is most efficient in waters containing NaCl, or you can say in marine conditions where the water is salty, and the reason is due to high conductivity of the solution. Okay, mechanism of electrochemical corrosion. So anodic reaction, we all know dissolution of metal takes place. As a result, metal ions are formed with the liberation of free electrons. See, for example, on the surface of the metal, some parts acts as an anode, and steel, okay, steel part acts as an anode, and this is the concrete part. Okay, in that, anodic part is here, cathodic part is here. So Fe, anodic oxidation, Fe gives Fe2 plus 2 electrons. So this current, and then from the atmosphere oxygen reduction reaction, 2OH minus, again it will form rust, FeOH twice. FeOH twice. Fe2 plus from here, and OH minus ion from the reduction of oxygen to OH minus. So we get FeOH twice, which, so first metallic Fe2 plus, then it converts to Fe3 plus. Okay, like that, oxidation of iron occurs like that. Okay. So this is the anodic reaction. Metal dissolutes to give metal ions and electrons. That is the anodic reaction. Okay, cathodic reaction, reduction. It may be hydrogen evolution. Cathodic reaction, which happens in the cathodic parts of the metal. It's either hydrogen evolution, which occurs in acidic medium, or oxygen absorption occurs when the solution is aerated sufficiently. Okay. See, in acidic medium or in basic medium, the reaction is given. In acidic medium, the reaction is different. In basic medium, it gives OH minus ions. So 2H plus 2 electron gives hydrogen. This is called hydrogen evolution reaction. This occurs in acidic medium. Whereas oxygen reduced to 2H2O in acidic medium, oxygen reduced to hydroxide ion in basic medium. Okay. So this is the reaction in cathodic part. Okay. Okay. First we will see hydrogen gas evolution. Wet corrosion takes place by the following two ways: hydrogen gas evolution or oxygen gas absorption. This type of corrosion occurs in acidic medium. For first we will see hydrogen gas evolution. So consider the metal iron. Anodic reaction is nothing but Fe gives Fe2 plus 2 electrons, oxidation. That is iron converted to iron 2 plus ions with the liberation of 2 electrons. Okay. The electrons released flow through the metal from anode to cathode, whereas the H plus ions of acidic solution are eliminated as hydrogen gas. Okay, this is in acidic medium. So H plus ions in the acidic medium are eliminated as H2 gas. Okay. So at the cathode, the reaction is 2H plus 2 electron reduction reaction gives hydrogen. Okay. The overall reaction is Fe plus 2H plus gives Fe2 plus hydrogen. Okay. All metals above hydrogen in electrochemical series have a tendency to get dissolved in acidic solution with simultaneous evolution of hydrogen gas. For example, we have seen zinc plus H2SO4 dilute gives zinc sulfate plus hydrogen. Okay. So this statement is from electrochemistry and this is the example. Okay. Next, mechanism of wet corrosion by hydrogen evolution, diagrammatic. So this is the anodic area large and this is iron metal. In that anodic area, iron anodic area large, this whole area, and small cathodic area is here. Okay, and this is diffusion of Fe2 plus into solution of electrolyte. This is acidic solution electrolyte. This is small cathodic area. Okay, so what happens? Iron undergoes oxidation reaction and hydrogen evolution happens due to the H plus ions in the acidic medium. Okay, H2H plus 2 electron gives hydrogen evolution. Okay, so this is the representation of electrochemical corrosion by hydrogen evolution. Absorption of oxygen. So for example, rusting of iron in neutral aqueous solution of electrolytes in the presence of atmospheric oxygen. Usually the surface of iron is coated with a thin film of iron oxide. If the film develops cracks, anodic areas are created on the surface because of film develops cracks, anodic areas are created on the surface. While metal acts as cathodes, it shows that anodes are small areas while the rest metallic parts are large cathodes. See, for example, anode area, okay, anode area smaller, cathode area larger, means it will undergo very severe corrosion because anodes provides electron, gives electron, okay, whereas cathode accept the electrons. So because of large cathode area, it accepts large electrons, so the metal has to undergo faster oxidation to provide the electrons. Okay, the released electrons flow from anode to cathode through iron metal. Okay, so at anode, for oxygen absorption of oxygen absorption mechanism of electrochemical corrosion, anode same, Fe2 plus, Fe metal gives metal 2 plus ions and 2 electrons oxidation. At cathode, of oxygen plus H2O plus 2 electron gives 2 OH minus reduction. Overall reaction is FeOH twice. This product called yellow rust. Okay, yellow rust, Fe2O3 dot. Okay, this is FeO. Okay, Fe O dot Fe2O3 will be black in color, which is nothing but Fe3O4. Due to excess of oxygens, it can happen. And Fe2O3 is what we call it as rust, which is brown in color, and it's a very common. Iron in, this is ferric, this is ferrous ferric. Okay, so this comes under the category of yellow rust, FeOH2. Fe is in +2 oxidation state, ferrous. Okay, so the diagrammatic representation, formation of rust in seawater. Okay, so what happens? O2 plus 2 H2O plus 4 electron gives OH minus. Okay, this is the reduction reaction happens. And iron, okay, gives Fe2 plus, and this is the this metal is getting corroded and formation of FeOH twice. Okay, so this is due to the oxygen from the atmosphere getting reduction, iron as an anode getting oxidized. Okay, so this is the reaction, oxidation, reduction, and this is the overall reaction due to which FeOH2 yellow rust is formed. Okay, with this this video is over. We will see in the next video the different types of electrochemical corrosion. What are the factors affecting the rate of corrosion? All those things.
Like, share and subscribe. Hit the bell icon for more updates.